Math 1314, Tyler Junior College, Section 5.1, 2x2 systems of linear equations, solving a generic 2x2 system. This is a little beyond where most college algebra lessons go, but you may have noticed in some previous videos that I like to try to make generalizations wherever possible. Now, this generalization is not brand new. It has been discovered a long time ago, and there are classes where this generalization is used. But I just wanted to show you how, as a thinking mathematician, to approach a problem generically, usually in an effort to build a formula or a shortcut to get to the answer. So yes, what we're about to do will answer the question, if I tell you these 6 numbers, can you calculate x and y? Now, how would we attack it generically? Well, the same way we attack it specifically. Choose a plan of attack and go through with it. Do you want to do substitution? Well, we could, but we would have to isolate any of these 2 letters, x and y, and no matter which one we isolate, our last move is going to be to divide by its coefficient, and we don't want to set up all those fractions unnecessarily. So let's not use substitution, let's use addition. Now, how can we possibly use addition? Because the plan with addition is to set up opposites. Well, first we have to pick a variable to set up opposites for. Let's just say that we want to eliminate the x's. Eliminate x. Let's rewrite the system here just for a second. Ax plus by equals c. Dx plus ey is equal to f. If we wanted to eliminate the x's, we need to make the coefficients match. But remember, we had a strategy for that. You can always set up an elimination on any variable by simply multiplying both sides by well-chosen numbers. And for well-chosen numbers, that means take the previously existing coefficients and reverse them as multipliers. We're going to multiply the top equation by d and the bottom equation by a. However, that will make them match exactly. We need them to be opposites. Let's multiply the bottom one by negative a. And let's see what happens. If we multiply the top equation by d, we get ADX, I like putting my letters in alphabetical order, plus BDY is equal to CD. If we multiply the bottom equation by negative a, we get negative ADX minus AEY equals negative AF. And remember, we just set up an elimination, an opposite pair for the x's. The x's cancel. On the y's, we get BDY minus AEY is equal to CD minus AF. How are we going to solve for y? There's 2 y terms and they're not like. This isn't the first time we've run into this situation, but I'll remind you how to get out of it. If we need to solve for y and we have unlike terms that both have a y in them, we can factor out the y. If we factor out the y, we get BD minus AE equals CD minus AF, and now we just divide both sides. Y is equal to CD minus AF over BD minus AE. In retrospect, I wish I had changed where I put the negative. I wish I had put the negative on the D, but I'll tell you the only consequence that would have happened is everything would have changed signs. Think of it this way, if I multiply both sides of this fraction by -1, positive things become negative and vice versa. This AF would become positive, so I'll write it first. The CD would become negative, so I'll write it second. This AE would be positive, I'll write it first. This AB would, that's not AB. It's B, oh, it's BD. Whoa, it's BD. Would be negative and I'd write it second. I'm going somewhere with this, you'll see, hopefully in just a moment. Actually, no, I'm not taking us that far, so either one of these would have been okay. But now we have a formula that says this is what y equals. If you know the 6 numbers, the coefficients in your system, the x coefficients, the y coefficients, and the constant terms, you can just stick those values here and poof, you got what y equals. But what about x? Well, we could substitute this mess back up there, but I really don't want to do that. If we want to find out what the formula for x is, let's just start over and eliminate the y. To eliminate the y, we would take the original system, ax plus by is equal to c, dx plus ey is equal to f, and let's focus on eliminating the y. Well, if we take their coefficients and reverse them, multiply the top equation by e and the bottom equation by b, that will set up matching terms, but we need them to be opposites. I'm not sure which of these I want. Let's make the bottom one negative. Yeah, the bottom one negative is what I want. That would give us on the top aex plus bey is equal to ce, and on the bottom we would get negative bdx minus bey equals negative bf. The y terms, as messy as they are opposites and they cancel. That leaves us aex minus bdx is equal to ce minus bf. And if you can picture the factoring move, well, let's just do it. Factor the x out of the left, you get x times ae minus bd equals ce minus bf, and then divide both sides. We get x equals ce minus bf all over ae minus bd. And if you notice, the denominators are the same. The only difference is the numerators. So we can, and we have, come up with a formula that will instantly solve the 2x2 system. It's messy. The x is the ratio of ce minus bf. The denominator is ae minus bd. The y has the same denominator, ae minus bd, but the numerator is af minus cd. If you start staring long enough, you'll see some patterns, but let's not stare too much. There is an approach that involves this and represents the generic solution a lot more cleanly, but it goes a little bit beyond what we're ready to discuss right now. So challenge yourself, especially when you have a technique that you can try to generalize, such as solving a 2x2 system. You might be surprised with how much you can accomplish. All right, that was fun.